hit the go button.
Make sure.
Good.
Sure. Just let me know.
Okay, gotcha.
So do you?
I'm gonna do this. Wait.
I'm just gonna see next time.
It's like 30 seconds. Okay, Jake, we're ready.
All right, good morning, everybody. My name is Young. This is John Ford, Isaac Christian, Eric Verduzco, and John Goldsmith. And we are the Baja Vehicle Suspension Validation Team. So here's the agenda for our presentation. I'm going to give a short introduction. Then John Ford is going to give the test bed setup, and Isaac Christian is going to talk about the drop test. And then John Goldsmith is going to talk about the static test. The FDA model validation was given by Eric Verduzco, and then I'll end the presentation with a summary. So, the Baja competition. What is the Baja competition? Basically, it's a college design series where colleges around the world come to compete in designing a single-seat off-road vehicle, recreational vehicle. So, as far as the frame and the suspension is concerned, the design is pretty loose, except for safety. But the engine is restricted. Everyone's restricted to the same engine, so therefore everyone has the same horsepower. So one of the advantages of going, one of the ways to go faster than your competitors is to be light. And that's where we come in. So the problem is, we want to be light enough that we're fast, but we don't want to be so light that suspension components will fail during the competition. As you can see here this happened all during the endurance race. Here, the rear suspension A-arm here failed during the competition. Here you can see that black component is an upright that basically holds the tire up, and they chose too thin of a material, and during the competition, the metal actually tore. So what we're going to do is we're going to try to find the actual forces that the suspension goes through, and then so we can design a lighter but still survive the competition. Next slide. So here's a project organization. So on the admin side, Dr. Hong was our project advisor. Alumni advisor was Kevin Nart. The captain of the Baja team is Alex DeGondo. And from the senior design side, I was the phase 3 lead. Strain gauge research was done by John Goldsmith. The test bed design was done by John Ford. FEA research was done by Eric Verduzco, and force transistor was done by Isaac Christian. All right, so here's a project overview of what we did. So basically, we did a drop test. We found the loads based on that drop test. Then we built a static test, and we put the forces that we calculated onto this component of the suspension components. Then we correlated that data with the FEA analysis. So here's the phase 3 deliverables. So basically, for this quarter, what we did was we set up the static test, we conducted the static test, analyzed the data, and we verified with FEA. So here is our requirements page. Basically, long story short, all our capabilities exceed our requirements. For instance, the drop test. We need to drop from 3 feet. We can lift the car up to 4.5 feet. The restraints for the static test need to withstand at least 2,000 pounds. The restraints were 5,000 pound ratchet straps. We only needed about 8 from 24 strain gauges, and we bought about 40. Next slide. So next, John Ford's going to come and talk about the test bed.
Hi, my name is John Ford. I'm going to talk about the test bed. Next slide, please. Okay, you can see from this picture, this is actually an overview. This is actually second quarter, so this is phase 2 for the drop test. And we actually utilized the forklift, and we had a quick release system that actually dropped the car. We used multiple 30-degree orientations on this, and we did about 3 times each. Like I said, this was on the first quarter, not actually this last quarter. Next slide, please. This is kind of a zoomed-in view. You can actually see right here the actual release system from the forklift. We had a cradle mount that was actually anchored onto the forks itself, and then from here, this would go down to a cable and pin shackle system that we had. The operator pulled it, and then the cradle mount actually caught the pin because we had some procedures where we didn't have that before, and the pin actually was flying towards the operator. It was eventually pretty bad safety hazard that we corrected. And the next picture right here shows that we verified each drop test at 2 feet before we actually dropped it. Next slide, please. It's a quick overview of the drop test equipment. We used a 3/4 shackle in right here. We milled out a piece of steel to actually fit the groove. So when we actually pulled it, it didn't inhibit it. It came out smoother. We had to lube it up. We used a plastic coated steel braided cable, so the operator when actually pulled the pin and dropped with ease. We used ratchet straps that were rated at 2,000, but together combined, it came out to 8,000 pounds each. To mimic the weight of an actual operator in the vehicle itself, we use all-purpose sands that weighed about 50 pounds at that. Next slide. For phase 3, the static test, which was this quarter, as you can see this picture overview, we needed to create 5,000 pounds of force actually pushing upward into each tire for each suspension members. We had some of the requirements for this. We needed a table that would withstand the forces going up, so we actually utilized an IV table at the lab that we had. We had to fasten the table itself to the ground and ensure that it wasn't going to create a moment or anything. Next slide, please. For the first conceptual design we actually, through the FEA analysis, we tried to use a point load, but this unfortunately didn't work. We kept having problems with the actual ball jack buckling, and it became a real bad safety hazard, so we had to quickly change that design. Next slide, please. This is the actual final concept design that we ended up using that was the safest. We actually, instead of a point load that we're trying to achieve, we actually made the load area bigger, so we go upward, and we used a bigger jack that was rated, I think, about 10 tons or something. Excuse me. And this actually was the most stable. We had no issues with the actual buckling, and it was actually quite successful. And we did see the loads that we needed for each suspension arms. Next slide, please. And up next is Isaac Christian with the drop test.
Hi, I'm Isaac Christian. I'm going to talk about the drop test. The first thing we did was to attach the axometers to the car, and we attached for the front tire, we did it on the kingpin, and we attached 3 axometers in the X, Y, and Z coordinates using a right-hand rule, and in the back spindle, we attached the axometers. This is basically the DAC we use for the axometer connections. The DAC had 4 connections, and we connected the X, Y, and Z, and the 4th axometer, which was not shown in the picture, we connected at the CG, which was for the driver's seat. And this was the power source and the cable that connected to the computer that gave us the readings. Before we did the actual test on the car, we did it on this block of steel, and so we can see how the axometer is read and how to use LabVIEW, which was the software that we used for the reading. And this was the actual drop test that we did. That was one of the drop tests we did. We did different drop tests at different angles, at 30-degree angles at different positions. And after we do the drop test, we use LabVIEW. And in the LabVIEW, there's a certain option that we can use axometers, and then you connect to all the points that were connected to the axometer so that we can get the readings. And then we set our configuration according to the axometer that we had, and the axometers we had a maximum of 50 and minimum of 50, so we set that as max and min. And we used our rate for 2.56K because after we did the drop test, we see a reading when we run the program, and after that we get a bunch of numbers, and then when we save it as a .tdms file, and then we open up in Excel, and we get a bunch of samples, and from that we can pick our max and our min. This was the results that we found. That for the flat, when it was flat, we found the 52 Gs in the front and 40.3 in the rear. This is front raised, means it was front raised like a 30-degree angle. Those are the numbers. The left raise was left. We left raised the car at a 30-degree angle. The right raise, we raised the right side at a 30-degree angle. The rear raise, we raised the car at a 30-degree angle from the back. And at the driver's seat, we found a CG of 18.7.
All right, well, I'm John. I'm here to talk about static tests, actually the strain gauges. So a strain gauge is basically a thin piece of metal that is wrapped up and coiled inside of a plastic filament or plastic sheet. And the way it works is these are set to specific resistances. The ones we were using were set at 350 ohms. And when the gauge is under load, the diameter of the wire is going to change. So that's also going to change the resistance that it sees. When the gauge is under tension, the wires become longer and the diameter becomes smaller and the resistance goes up, and conversely, when it's under compression, the diameter gets larger and it's less resistance in there as well. The gauges, there's multiple different ways to wire the gauges together. There's the quarter bridge, half bridge, and full wheatstone bridge. In our experiment, we opted to use the half wheatstone bridge, one because of cost factors, but also because it allows to do tensile and compressive forces at the same time. And on top of that, it's going to allow for the temperature fluctuations as well. Next. So the next step, what we had to do is basically verify that we're getting valid readings out of the strain gauges. So we set up a small test bed over here, and basically we did a measurement and calculated what the strain was going to be. And the strain comes out as the strain is the moment times the distance to the center of mass divided by the moment of inertia times its modulus. And when we did the hand calcs from the strain readings when we were getting through LabVIEW, we were getting about a 15% deviation out of it. So basically we had to, when installing all the strain gauges, we had to prep the surfaces and get everything ready for the gauges themselves. And in order to do that, we had to clean all the surfaces up, mark the locations where we're going to be putting the strain gauges, adhere them down, and then solder in all the wires. And on top of that, after I also ended up gluing, using hot glue and securing all the wires and fasteners down. That way there was a lot less force on the actual gauges themselves, and it made it a little more of a robust setup. So this is basically how we had our setup for the strain gauges. We used the 10,000 pound jack in conjunction with the force transducers. And what that did is when we jacked it, it allowed us to get to the desired forces that we wanted to actually get our readings from on the suspension. So when we did the actual testing, this is basically what we saw. On the front arms, the majority of the three, because we had 4 different setups on there, the only one that's actually saw a strain was the front lower arm, and that was the one in bending, and that was in the vertical forces as well. The other 3 locations saw very, very minimal strain, which actually makes sense because it appears to just be in rotation, so it really shouldn't see much strain. Same thing in the rear suspension. When we loaded it up, the only arm that actually recorded a decent amount of strain was the rear trailing arm, and that one was just exactly the same in the vertical forces where we expect to see them from the bending and compression. And same thing, the rest of the trailing and control arms didn't see much, and just like in the front, makes perfect sense because it's mostly in rotation as well. And here's Eric with FEA.
Okay, so I'm Eric. I was in charge of doing FEA analysis. Okay, so we want to create a model so we can verify that we actually see strain on these suspension members. So in SolidWorks, we first started and created all the suspension links, so the A arms, the bottom and top, and the rear suspension links. Next, what the SolidWorks does, it creates the model. Creates the model, and then it breaks up your model into very small portions called finite elements. At these elements, nodes are created, which as you join together, it could give you different readings. When you apply the load, you could get a strain, and once you have strain, you can also get stress. SolidWorks also gives us the option to choose how applying our meshes. What the mesh size does, it creates even more nodes. The more nodes you have, the more accurate your results can get, but that's only for certain models. Some models, you just need a coarse mesh and you'll get the exact same results. So for our simulation, we had to choose motion analysis because that was the best one for our situation that we could use. Some pros and cons. Some pros that we could actually assemble the whole model using only mates, and we could choose which parts to analyze. When we have the suspension, we have to include the shocks, the kingpin, the rotor, and if you have all that and try to mesh it, it's going to take forever. So for our analysis, we just focus on the suspension components. It's also time dependent, so we could choose how long to run the simulation. In a real-time animation, which actually shows when we apply force, how the wheel moves up and down throughout the suspension members. Some cons are that we cannot modify our results chart, which means that at certain sharp edges, you get the max stress, but we're not interested in that. We're interested in the actual A-arms and where we actually see the max stress. We also don't have the tool, the Pro Tool, which what that does, that we could actually choose a certain node and know the strain that that specific node has, but we don't have that option either. So here we have the SolidWorks, the graphics interface. As I mentioned, it's time dependent, so we can choose how many seconds we want to run it. We also have the spring. We calculate our spring rate by actually taking our shock apart and applying weight on our springs to see how much they compress. The force, we apply it at the bottom of the tire, and that force is what we calculated using our accelerometers. We have the contact. What the contact does that when two objects hit each other, they actually don't keep going up. In the real world, that would mean the shock is actually bottoming out. We have gravity and our FEA analysis. So here are results. So for the front, we have the A-arm, the bottom A-arm, the top A-arm. The bottom one, as my team member mentioned, sees most of the stress. So we could correlate our strain results by looking at the chart above. The gray line represents how much is strained on the bottom A-arm. We have the side view, which we can see that the max strain is at the top and bottom, and it correlates with the gray line, and the yellow and blue represents the vertical strain. And as you can see here, there's the blue area between the top and bottom. It's blue, which means there's very little strain there and very little stress. So now the rear. The rear was quite difficult because in SolidWorks, it actually thinks everything is perfect. So all the angles, everything, all the mates I created, they actually go up and down. But in real life, the bottom trailing arm, it's at an angle, so it was kind of forced in and it was bolted on. So from those results, we could see that this little angle could create that small amount of strain that we see, which we shouldn't see any strain, any tension. We should only see tension and compression forces on the rear links because it's a bi-member. And that's pretty much it. And now John's going to give a summary.
All right. Okay, to summarize. So for this quarter, what we did was we designed and built the static test bed. We attached strain gauges to the suspension members, and we measured the strain in the suspension under load. We calculated the stress based on the strain, and then we validated our CAD model. This way, even though that this car is not the actual car that they're going to go out and compete with, we validated the CAD model, so we can put an input into the CAD model, and we'll know that that's actually what's happening to the real car.